Hello everyone. In this video, we will be discussing distributed transactions. Let's get it started. In a monolith, we have single database having multiple tables. This can be seen in the image where this is a monolithic database. And I have three tables. Table 1 is for payments, table 2 is for notification, table 3 is for orders. We can put a lock on relevant rows and then process logic and finally commit the transaction. But in a distributed system, where multiple microservices, which have the potential of having different databases owned by different teams, are running, we have to make sure either the transaction is successful or it is rolled back, which may be after some retrying. For example, in the another image you see, there are three services. One is the order service, one is the notification service, and one is the payment service. You see that each service is having its own database or its own tables maintained in their own databases. So here we have three services and hence we have three databases having three tables. In the above, you see that we have only one database, but we have three tables. So a monolithic system generally has a single database, whereas in microservice architecture, we have generally a dedicated database for each of the service. So how do we ensure a distributed transaction where we ensure that either the transaction across all the services is successful or it is rolled back? We want atomicity in a distributed system. So let's say you place the order. This is the first thing. Placing the order requires you to do a payment. Once the payment is done, you want to notify the user. Now let's say the payment service failed. Then not only payments record should be rolled back, the transaction should also roll back your order. So this should also be rolled back. So this rolling back is coming under the topic of distributed transaction. So there are some popular approaches and we will be discussing two of them. First is the two-phase commit, also known as 2PC, which stands for two-phase commit. As the name suggests, this commit is done in two phases. What are those phases? The first phase is we have another service called coordinator, which asks each service in phase 1 if they are ready for second phase. This is the voting phase. This coordinator service will ask each service involved. For example, it will ask the order service, it will ask the payment service, it will ask the notification service if all of them are ready for the second phase. If they say yes, then a second phase is started, where if all services response yes, this means all the services, then lock is put on relevant rows and transaction is processed. This is the commit phase. So the first phase is voting phase and the second phase is the commit phase. What are the cons of this? The cons of this is in large databases, having lock for such a large time can be problematic. This is the problem known as long living transaction problem. For example, let's say the traffic is too much. Let's say this is a system of Amazon and it is a Black Friday sale. Now, if you see a lot of transactions, so that means we will be putting lot of logs. And if some transaction is living, spanning across multiple databases, then it will take at least, let's say, half a minute to execute. This half a minute can be deteriorating to the system where other transactions cannot process those rows because the lock is there in that duration. So this is first con. The second con is in second phase services can go down. What if in the voting phase all the services responded yes? But while the execution of the second phase, one or two services went down. So that's why we seldom use this approach. Especially in large systems, we avoid two-phase commit approach. But it is always good to know what a two-phase commit is. Two-phase commit is separate from 2PL, which we discussed in the distributed concurrency control video. If you have not watched that, the link is in the description. You can go ahead and watch that as well. And if you have not subscribed to the channel yet, I would request you to subscribe because this will send you a notification every time and I upload a video, and it will keep you updated with the software engineering domain. Let's move ahead. The second approach is the Saga approach. On completion of a transaction step, publish a message. Publishing is nothing but a generation of event to trigger the next transaction step. So basically, we are relying on the events generation for the communication purpose so that other service can pick up that it has to start the second step. For example, consider a use case. User is trying to purchase something on Amazon. So they do the payment, order is processed, and they get the notification. Basically, confirmation of the order. Say payment is done, but assigning items to user's order fail. Let's say payment was done. Let's say you were deducted by 100 rupees. But the time the order was assigned to the user, there was some inventory glitch. Let's say item was not available or some service failed. This is not an ideal experience. So what should be done? First way is we roll back the entire transaction by undoing the changes. This is the backward recovery where we will refund the user of the deducted amount. The second way is since the payment is already done by the user, can we do a retry? This is known as forward recovery. In large systems, some part may be using way 1, that means backward recovery, and some part may be using way 2, which is the forward recovery. There are two popular approaches for this. One is the orchestration and one is choreography. Both come under the Saga pattern. So if someone asks you what is Saga pattern, you will have to discuss two things. One is the orchestration, one is the choreography. Let's first discuss orchestration, the first approach. Orchestration is command and control way. If you have seen an orchestra, there is a coordinator who is sitting or standing in between of all the musicians. For example, this is a popular image from Mr. Bean. In this episode, Mr. Bean gets the stick and he starts waving it, and musicians start playing. So he is actually acting as a coordinator where he is sending the commands and controlling the musicians. Similarly, there is an orchestrator microservice or the coordinator, and it coordinates between the services: payment service, order service, and notification service. Now, what are the pros? If something goes wrong, we can know looking at the orchestrator logs where issue might be. So this orchestrator is communicating with all the services. In this diagram, 3 services are there. If something goes wrong, this orchestrator will be having the logs, which will be helpful for debugging purpose. The second approach is choreography. You know that a choreographer trains the dancers and verifies they are doing good step, and then does not command them in the real performance. So let's say some movie is being shoot, and before the movie is shoot, the actors learn the dancing steps. So there is a choreographer, let's say Prabhu Deva, and he is teaching the actors that you have to do this step when this part of the song plays. So they train them, but he does not command them in real shooting. Similarly, in this approach, system is verified and working as expected, and then microservices coordinate without any external service. So while building the microservices itself, it is monitored and designed in such a way that they will work as expected. And in the real production, they are not controlled by any other service. Orchestration, we were seeing that there was an orchestrator microservice. We do not have such a provision here in choreography. So each microservice emits the events and other service listen to those and act further. For example, I am a I am going to buy something on Amazon. So I do the payment. As soon as payment is done, event is generated, which is picked up by order service. That payment is done. Order service assigns me the order and then generates item added to order event, and which is picked up by the notification service, and I get the notification. So these are the events, event 1 and event 2, which are generated by one microservice and picked up by another. What are the cons of this? If something goes wrong, it is very difficult to know where flow went bad. We need really good observability. What if something goes wrong here? After payment, the order service was not able to pick up. Order service did not receive the event. If the event was received, order service was not able to process. What went wrong? It is very difficult to get this judgment because in the orchestration methodology, we were having the logs in the orchestrator microservice. Here we do not have any centralized service, so it is very difficult to debug. So how do we debug? The debug part in distributed services is done using a correlation ID. So a correlation ID is used to debug the distributed transaction failures. It is a unique identifier that follows a request as it moves through the different services, usually by including it in the HTTP headers or message. So there is an ID which is generated and which travels through whole the distributed transaction. And using this, you can get the logs across all the microservices. And this ID is known as correlation ID. We can filter a type of requests based on this correlation ID, the things we just discussed. Each service logs the correlation ID along with other relevant information, allowing us to trace the request through different services. So that's all in this video. If you're liking the series on system design, microservices, and distributed systems, I keep making videos on such topics on AI, Java, interviews. So you can subscribe to the channel. Consider sharing the video and liking it. If you have any topic in mind which you are finding hard to understand, please feel free to comment on the video. And thank you so much.